11 of the course Thermodynamics. This is your tutor Pragya Sahu, PMRF scholar at Department of Chemistry. Okay. So in last class we started with the second law of thermodynamics, and after that we studied some of the statement of the second law of thermodynamics, where we studied the Planck statements, okay, the Kelvin Planck statement, the entropy statement, and all. Okay. So today I'll start with the Clausius statement. So, according to this statement, it is impossible to transfer heat from a cold reservoir to a hot reservoir without doing some work. Okay. So, what this statement means that it is impossible for us to transfer heat from a cold reservoir to hot reservoir without doing some work. So, we will have to apply some work if we want to transfer heat from a cold reservoir to hot reservoir. Okay. So, let us say this is your cold reservoir. Okay. So in order to transfer heat from this cold reservoir to hot reservoir, where the Clausius statement says that it is impossible for us to transfer the heat from a cold reservoir to hot reservoir without expenditure of some work. So now let us solve a problem, which is if an automobile engine burns petrol at a temperature of 800 degrees Celsius, and if the surrounding temperature is 21 degrees Celsius, then calculate its maximum possible efficiency. Okay, so this is the question where this automobile engine burns petrol at a temperature of 800 degrees Celsius. Okay, so the temperature, that is your TH, 800 degree Celsius. Okay, and it is transferring heat to the, that means surrounding, and its the surrounding temperature is your, that is TC is your 21 degrees Celsius. Okay, so now we are asked to calculate its maximum possible efficiency. So in order to calculate the efficiency, what formula? So in last class I have told you that the percentage efficiency can be calculated using this formula, where this percentage efficiency is equal to TH minus TC divided by the TH and multiplying the whole with 100. Okay. So where TH is the temperature of the hot reservoir, your TC was the temperature of cold reservoir. So here your TH is 800 degrees Celsius and 816 degrees Celsius, and your TC is 21 degrees Celsius. So let us first convert them into the Kelvin. Okay, so if we want to convert them into Kelvin, what we will do? We will just add 273 to them. So what will become? 1089 Kelvin. Okay. Next, if we add 273 to this 21, what will it become? 294 Kelvin. Now we have converted these degrees Celsius into Kelvin, and we know TH and TC. So let us just put this value in this equation. Here TH is your 1089 Kelvin minus your TC was 294 Kelvin, and again dividing it by TH, which is 1089 Kelvin. Okay, so and multiplying the whole with 100. What will you get? Your 1089 minus 294, and if you subtract this and divide it with 1089, and the result you will multiply with 100, so you will get 73. Okay, so if this value is 73, then what will you get? That means your percentage efficiency is 73%. Okay, so that means the maximum possible efficiency of the automobile engine is 73%. So this is your answer. Okay, which is 73%. Okay, now let us move to the next slide. So in this slide, we will read the spontaneity and randomness. So before that, let us just note one point, that is, what is the unit of entropy? So the entropy, which is denoted by S, denoted by S, okay? This is equal to the heat energy exchange divided by the temperature. So this was the, in the last class I have told you that your S is equal to Q by T, that is the heat energy exchange divided by your temperature is the heat energy exchange divided by the temperature at which the exchange takes place. So at which temperature this exchange is taking place? Okay, right? So the SI unit of entropy will be the SI unit of entropy will be, so your S is equal to Q by T. So what the unit of this is Joule and this is Kelvin. So your SI unit will be Joule per Kelvin. Okay. So this is what I had tell you. Okay. So now let us read what is spontaneity and randomness. So the careful examination shows that in each of the process, like melting of ice and evaporation of water, okay, the melting of ice or the evaporation of water. So if this is in this process, what is happening? There is an increase in the randomness or disorder of the system. Okay. The water molecules in ice are arranged in a highly organized crystal pattern, which permits little movement. But when this ice melts, the water molecules become deorganized and they can move freely now. So the movement of molecules becomes in the liquid phase and even more free in the vapor phase. So if your water ice is changing into water and then changing into the vapor, that is your gaseous phase. So what is happening over here? The randomness is increasing. Okay. Okay, because your molecules are freer in the liquid phase, and they are even more free to move in the gaseous phase. Okay, so in other words, we can say that the randomness of the water molecules increases as ice melts into water or water evaporates. So both are spontaneous processes. So this changing this process, that is where the melting of ice into water and the evaporation of water into vapor, they are all the spontaneous process, and they result in the increase in the randomness, that is entropy. Okay. So what they try to say here, that let's say you have ice. Okay, so this is your ice cube. Okay, now let's say you melt it. Okay, and at what temperature it happens? 0 degrees Celsius. So here ice is melting into liquid, that is your water, which is in liquid phase. Here your ice is in solid phase. So in conversion from ice solid to liquid state, what is happening? In solid phase, your molecules are organized. Okay, so the water molecules in ice are arranged in a highly organized crystal pattern. Okay, so they are organized in a, they are highly organized. Okay, like this. But when it is changing from the solid to liquid phase, the water molecules become deorganized and they can move more freely, because here it is your liquid phase and they become deorganized, and now they can move randomly. Okay, they can move freely. And if we provide 100 degrees Celsius, that is the boiling temperature, what will happen? This water will evaporate and will turn into gaseous phase. Vapor will form. So in that case, your water molecules will be more free to move. Okay. So what is happening from in going from solid phase to liquid phase to gaseous phase? So here the randomness is increasing. Randomness is increasing, which means entropy means what? Randomness. So that means your entropy is increasing. So in going from solid to liquid to this gaseous phase, your entropy is increasing. So here they have written simply that we can say that the randomness of the water molecules increases as we go from ice to water and to its vapor. And these processes are like the transitions from solid to liquid and liquid to gas. These processes are spontaneous processes. Okay, from solid to liquid to gaseous phase. So these are spontaneous processes. Spontaneous means they will occur directly. Okay, so and this will result in increasing the randomness. So what is happening? The randomness is increasing. Okay. So here spontaneous means it will happen immediately. Okay. Now let us move to the next slide. Here, this is a conical flask, and here this is crystalline solid. this crystalline solid, and it is getting transit, and after the transition it is becoming this liquid which after transition forms the gaseous. Here, in going from solid to liquid, what is happening? The randomness is increasing. Okay, the randomness is increasing. That means your entropy is increasing. If entropy is increasing, that means your delta S will be greater than 0. Okay, because here entropy, that is randomness, is more than here. So if you subtract it, then the value will always be positive. That means your change in entropy will always be greater than 0. Here, if we go from liquid to gaseous phase, here the molecules can move more freely. That means here there is more randomness. So more randomness means the more will be the entropy. So from if you go from liquid to gaseous phase, your entropy will be more. That means your entropy will increase. So if you take the difference, your delta S will be greater than 0. Means your delta S will be greater than 0. Okay, this is written over here. Here it is shown that if this is ice, okay, so here they are arranged in a very so here in the case of ice, they were arranged in a proper manner. So when it melts, now they are not organized. Okay, so in that case, there is randomness. So that means your entropy will increase. Okay, okay. So this is shown over here that your here in case of your ice, the entropy was low, and in case of water, entropy was high. So if you subtract them, that means your entropy is increasing. So if you subtract them, your entropy will always be greater than 0. That means it will be positive value. So what is the standard entropy change? It is possible to calculate the actual entropy of a substance at any temperature above 0 Kelvin. That means you can calculate the actual entropy of a substance at any temperature above the 0 Kelvin. The absolute entropy of a substance at 290 Kelvin, 298 Kelvin and 1 bar pressure, the standard entropy, the absolute entropy of a substance at 298 Kelvin, that is 25 degrees Celsius, and 1 bar pressure. Okay, so this will be called as the standard entropy. And the third law of thermodynamics states that which is was given by Nernst, and it states that the absolute entropy of elements is 0 at 0 Kelvin. That means in a perfect crystal, the absolute entropy of elements will be 0 at 0 Kelvin, and the standard entropies of all substances at any temperatures above 0 Kelvin will always have a positive value. So it means if you are taking the absolute entropy of elements at 0 Kelvin, then it will be 0. But if you are taking the absolute entropy of any substance above 0 Kelvin, then it will also always have a positive value. That means that S naught, that is standard absolute entropy, will always be greater than 0. Okay. This will not be standard entropy. This will be the absolute entropy. Okay. S. Because your standard entropy is what you calculate at 298 Kelvin. So this is the absolute entropy, which is greater than 0. Okay. So if you take it above 0 Kelvin, then it will have a positive value. So once we know the standard entropy of different substances, then we can calculate the standard entropy change for a chemical reaction, which is denoted by delta SR. So standard entropy change of a reaction, you can calculate if you know the standard entropy of the elements, then you can calculate the standard entropy change of a reaction, that is denoted by delta SR. Okay. Okay. So the standard entropy of reaction can be calculated by this equation, which is the standard entropy of reaction, which change in the standard entropy of reaction is equal to the summation of standard entropy of the products minus the summation of the standard entropy of the reactants. The reactants. Okay. So this is the equation we will use. So what is standard entropy of formation? So the standard entropy of formation is defined as the entropy of formation of 1 mole of a compound from the elements under standard condition, and it is denoted by delta SF naught. So your delta SF naught is your standard entropy of formation, that is defined as the entropy of formation when 1 mole of compound from the elements under the standard condition. Okay. So the entropy of formation of 1 mole of compound from the elements under the standard condition will be called as the standard entropy of formation, and it is denoted by delta S naught F. So we can calculate the value of standard entropy of element. Let us solve this problem where it is given that calculate the standard entropy change for the following reaction. Given the standard entropy of CO2 gas, carbon solid, and oxygen gas as 213.6, 5.740, and 205 joule per Kelvin respectively. So let us calculate this. So the standard entropy of the following reaction. The reaction given is this one. Okay. So what will be the standard entropy change of the reaction? So the standard entropy change, which is denoted by delta S naught R, will be equal to the summation of S naught of, that is standard entropy of products, minus summation of standard entropy of reactants, which will be equal to, the on product side we have carbon dioxide, that means standard entropy of carbon dioxide, minus on reactant side we have carbon in gaseous state, that means we will have to add the standard entropy of carbon, and we have oxygen also, so we will add the standard entropy of the oxygen. Okay, so if we put these values, what we will get? Standard entropy of carbon dioxide is given 213.6 minus standard entropy of carbon is 5.740 plus the standard entropy of oxygen is 205 joule per Kelvin. If you solve this, you will get 213.6 minus 210.74, and if you do this, you will get standard entropy of the reaction as 2.86 joule per Kelvin. So the standard entropy change for the following reaction will be, the standard entropy change for the following reaction will be is 2.86 joule per Kelvin. So this is your answer. Okay. So in this problem, we had to calculate the standard entropy change for the reaction, and we just applied this formula. Okay. And after that, we just put the values and did the calculation and get our answer. Let us move to the next slide now. Okay. So this is the entropy change. What if the entropy change is occurring by accompanying the change of phase? So when there is a change of a state, like phase, like from solid to liquid or liquid to gas or solid to gas. Okay, so when there is a change of a state from solid melting, liquid to vapor, that is evaporation, or solid to vapor, that is sublimation, then there is a change in entropy, and this change in may be carried out at constant temperature. Okay, so like for example, your the change of ice into liquid, that is your water, in liquid phase, what will happen? So this happens at a same temperature at 0 degrees Celsius. So this change may be carried out at a constant temperature reversibly as two phases are in equilibrium during that change. Okay. So there is a change of state from solid to liquid, liquid to vapor, and solid to vapor. Then there is a change in entropy, and this can be carried out at a constant temperature. So if that is the case, what will be your delta S? So in that case, your delta S will be Q reversible divided by temperature T, which means that you know that your Q reversible will is equal to delta H. So it will become delta H reversible at constant temperature. Okay? So now let us see what is entropy of fusion. The heat absorbed when 1 mole of a solid melts at its melting point reversibly is called molar heat of fusion. This we have studied in our earlier classes, that the heat absorbed when 1 mole of solid melts at its melting point reversibly, that is called your molar heat of fusion, and the entropy change for this process is called the entropy of fusion, and that is given by delta S fusion enthalpy change. In that case will be called as enthalpy of fusion, that is molar heat of fusion at a melting point. So here T will be your melting point, because your solid is melting and getting converted into liquid. Okay, so in that case, your change in entropy will be called as the entropy of fusion, and your delta H will be the molar heat of fusion, and T will be here your melting point. So this is how you can calculate the entropy of fusion. Here your delta H fusion is molar heat of fusion, and T is your melting point. Okay. Now let us study what is entropy of vaporization. Vaporization means what? Your liquid is getting changed into its vapor phase, in gases. So the heat absorbed when 1 mole of liquid is boiled at its boiling point reversibly is called molar heat of vaporization. And in that case, the entropy change will be given by delta S vaporization will be given by delta HV, that is molar heat of vaporization, divided by TB. Here TB is your boiling temperature, that is boiling point. So here delta HV is your molar heat of vaporization, and your T here, that is your temperature, is your boiling point. Okay. So the entropy change you can calculate using this equation. So now what is entropy of transition? So the heat change when 1 mole of a solid changes reversibly from one allotropic form to another. So at this temperature is called transition temperature, and the heat evolved is called as the enthalpy of transition, and the entropy change in that case can be calculated using the formula delta S transition, that is delta S T is equal to delta H of T divided by T, where your delta HT is your molar heat of transition here. Transition, and your T is your transition temperature. Okay. So these are different type of the transition that we studied. Okay. So now let us study the Gibbs free energy. One of the important applications of the second law of thermodynamics is to the spontaneity of reaction under a specific set of conditions. So, according to this, the most important application of the second law of thermodynamics is that we can predict the spontaneity of a reaction. So, a reaction that occurs under the given set of conditions without any external driving force is called a spontaneous reaction. So what do you mean by a spontaneous reaction? So let us say a reaction is happening without providing any external force. Okay, you don't have to work for that reaction to occur. Okay, so this reaction is occurring without applying any external force. So in that case, we call that reaction as a spontaneous reaction. So this type of reaction occurs spontaneously. Okay, we don't need to apply any force, any external force. Okay, so this reaction that occurs under a given set of conditions without any external driving force called a spontaneous reaction. Otherwise, it is said to be a non-spontaneous. Non-spontaneous means we will have to apply some external force in order to make that reaction occur. Okay, so in our daily life, we observe many spontaneous physical and chemical processes, which include the following examples. For example, so in our daily to daily life, we observe many physical and chemical processes that are spontaneous. Like a waterfall runs downhill but never uphill. Okay, so let us say this is a waterfall. It always goes from here, here to here, not from here to here. Okay, not the uphill. Okay, the downhill is what we observe always, not the uphill. Okay, the reverse direction. Okay, so we always see the waterfall runs this downhill, not the uphill. That means in reverse direction, and this is spontaneous. Okay, so this is a spontaneous process. The next one is a lump of sugar dissolved spontaneously in a cup of coffee, but you can it never reappears in its original form spontaneously. So let us say this is your coffee, okay? And you put some sugar cubes. What will happen? These sugar cubes will be dissolved in the coffee. So now, can you get these sugar cubes back? No. Okay. So, but it can never here what is it written that, but never reappears in its original form spontaneously. So, the process of dissolving of sugar, that is, you're dissolving sugar cubes into a cup of coffee. That process is spontaneous, but the process where you can get the sugar cubes again, that is non-spontaneous. Okay, that cannot happen. This process is spontaneous. Let us look at another example, that is heat flows from hotter object to a colder one, but never flows from colder to hotter object spontaneously. Okay? So this was also the statement of the Clausius. So where you, it is impossible for to transfer heat from a cold body to hot body without expenditure of work. Okay, so this is the same statement that the heat flows from a hotter object to colder one, the hot to cold, and this process is spontaneous. This happens spontaneously. Okay, but it can never flows from colder to hotter body without expenditure of work. Okay, so this process is spontaneous, but the reverse is not. Next one is the expansion of gas into evacuated bulb in is a spontaneous process. Okay, so let us say you have two bulbs and they are connected by a knob. Okay, so this bulb is filled with the gas. Now, if you move the knob, that means now first it was in closed condition. Okay, now if you move the knob, it will open. So what will happen? This gas will expand into this bulb. So if that happens, what will happen? Your gas will expand into this bulb. Gas will also come be here, and it will be distributed. So this process of expansion is spontaneous. This is expansion of gas. This is spontaneous. But is it possible to to reverse the process? Like, if do you think like you can reverse this process? No. So the reverse process, that is gathering of all molecules into one bulb, is not spontaneous. The reverse process is not spontaneous. Okay, so we will hear from this example. If you are on top, okay, like on a cliff, so jumping will be easy for you. So here it is spontaneous because you can easily jump from here. But if you are doing mountain, if you are mountain climbing a mountain, okay, so in case of mountain climbing, you will have to uh, you will have to work. Okay, so in order to climb the mountain, you will have to expend some energy. So in that case, it requires work. Okay, so this is non-spontaneous. However, this is spontaneous because you can easily jump from a top. So let us see the next example, which is the heat flow. Let us say first, this one is at 200 degrees Celsius and this one is at 100 degrees Celsius. Okay. If you just leave the knob open, so what will happen? The temperature will become equal. Like, what will happen? The heat will flow from higher temperature to low temperature. So this is what we have studied. So if heat is flowing from hotter body to colder body, okay, so what will happen? They will reach an equal temperature, that is 150 degrees Celsius. But this process is spontaneous. However, if you want to increase the temperature of this to 200 degrees Celsius, it cannot occur spontaneously. You will require energy. So it will require work. So that means this is work. This process is non-spontaneous. Okay. However, from going to this to this is spontaneous. Okay. The reverse is non-spontaneous because it will require work. Next is the gas flow. In the last example, I've just shown you that here this is a bulb having gas. If you open the knob, here this is in closed condition, and this is So there is no gas in it. Okay. So if you open the knob, what will happen? There will be the expansion of gas into this bulb. So they will be distributed into this bulb also. But if this process is spontaneous, but if you want to make all the molecules in one bulb only, so in that case you cannot do without expenditure of any work or doing require some and extra energy. So that process will be your non-spontaneous. Okay. So this example shows that the processes that occur spontaneously in one direction cannot take place in opposite direction spontaneously. Okay. So with these examples, we know that are the spontaneous processes, what are non-spontaneous processes. Okay. Let us move to the next slide now. Similarly, a large number of exothermic reactions are spontaneous. Okay, so an example is your combustion of methane. Methane is your CH4, and combustion means we are burning it in presence of dioxide and water. So if we balance this reaction, we will get this. Here, your delta H naught, that is the change in enthalpy of reaction, is equal to minus 890.4 kilojoule per mole. So this is an here minus sign shows that this is an exothermic reaction. If this is the case, that this reaction is exothermic, that means the reaction is spontaneous. So this reaction is spontaneous. That means your combustion of methane is an spontaneous process. Another example is your acid-base neutralization reaction, that is H plus OH minus will give water. This is your neutralization reaction. Here, you know that the change in enthalpy of the reaction was minus 57.32 kilojoule per mole. So here again negative, that means exothermic reaction. That means this process will occur spontaneously in one direction. Okay. However, some endothermic processes are also spontaneous. So here exothermic reactions were spontaneous. That doesn't mean that your endothermic processes or reaction will not be spontaneous. There are some examples where the endothermic processes are also spontaneous. For example, the dissolution of the ammonium nitrate in water is a spontaneous process. That is, the ammonium nitrate dissolves in water spontaneously. So, though this dissolution is endothermic. Okay. So, what is the equation? Your ammonium nitrate dissolves in water and forms your these ions. This reaction is an endothermic reaction, that is your delta H naught is 25 kilojoule per mole. Here positive means this is an endothermic process. If the process is endothermic, however, the process is endothermic, it is a spontaneous. Okay, so this is a spontaneous process where your ammonium nitrate dissolves in water. From the above examples, we can conclude that the exothermicity favors the spontaneity but doesn't guarantee it, because we see that here the exothermic reactions where spontaneous, these are spontaneous, but they do not guarantee, but the exothermicity of a reaction doesn't guarantee the spontaneity of the reaction. Okay, so we cannot say if the reaction is exothermic, that means it will be spontaneous. Okay, so we cannot decide whether or not a chemical reaction will occur spontaneously solely on the basis of the energy changes in the system. Okay, so we cannot say only on the basis of the energy changes in the system whether the reaction will occur spontaneously or not. So in that case, the second law of thermodynamics introduces another thermodynamic function, that is Gibbs free energy, which finds useful in predicting the spontaneity of reaction. So in that case, the second law of thermodynamics gives us another thermodynamic parameter, that is Gibbs free energy parameter, which will be useful in predicting the spontaneity of reaction. That means whether a reaction will be spontaneous or not. So the Gibbs free energy was developed in 1870 by Josiah Willard Gibbs, and he originally termed this energy as the available energy to do work in a system. So Gibbs free energy is the available energy in a system in order to do work. Okay, and this quantity is the energy associated with the chemical reaction that can be used to do work, and it is defined as below. So this was the statement that it is equal to H minus T into S. That is, H is your enthalpy, T is your temperature, and S is your entropy. Here, the Gibbs free energy is an extensive property. Okay, so that means you can add it or subtract it, and it is a single valued state function. Okay. Now, let us consider a system which undergoes a change of state from state 1 to state 2. So this is state 1 to state 2. And this is happening at a constant temperature. Your temperature is constant. So in that case, in order to calculate the Gibbs free energy change, let's say initially it was G1 and finally it was G2. So the Gibbs free energy change will be your G2 minus G1, that is final minus initial, and that will be equal to your H2 minus H1. You know that your G is equal to H minus Ts. Okay, so if you are calculating the change, this will be equal to delta G, that will be equal to G2 minus G1 change. So in that case, your G2 minus G1 will be equal to H. The final H will be H2 minus H1, and this is happening at a constant temperature, so your T will not change, but your entropy will change. So entropy will change from S1 to S2, so the change will be equal to S2 minus S1. Your delta G2 minus G1 will be denoted as delta G, S2 minus H1 as delta H minus T, and S2 minus S1 as delta S. So your delta G will become delta H minus T delta S. So if a system is undergoing a change from state 1 to state 2 at a constant temperature, then your Gibbs free energy change will be equal to this. That is delta G equal to delta H minus T delta. Now let us consider how this delta G is related to the reaction spontaneity. So we really want to know how this delta G will give us will let us know that how whether a reaction is spontaneous or not. We know that your delta S total, that is delta S system plus delta S of surrounding, your delta S total is equal to your change in entropy in the system plus change in entropy in the surrounding. So in that case, for a reversible process that is in equilibrium, the change in entropy of universe is 0. So for a we know that for a reversible process, the change in entropy of universe or total is equal to 0. So if that is the case, this is 0. This will become, this means your delta S system plus delta S surrounding will become 0. So this means your delta S system is equal to minus of your delta S surrounding. That means whatever the change in the system, it will get transferred to the surrounding. Okay. Similarly, for an equilibrium process, your delta Z equal to 0. And for a spontaneous process, your delta S total is greater than 0. That means we know that in a spontaneous process, your entropy always increases. So if entropy is always increases, that means your delta S total will be greater than 0. And if your delta S total is greater than 0, that means your delta S total is equal to delta S system plus delta S surrounding. That means your delta S system plus delta S surrounding will also be greater than 0. Okay, that means for a spontaneous process, the delta S system plus delta S surrounding will be greater than 0. Your delta S surrounding is equal to delta S system divided by T minus your delta S of system. Okay, so what will it become? So if we solve this, you will get delta S system minus T delta S system is greater than 0. If this is greater than 0, that means your T delta S system minus delta H system, this will be less than 0. We are reversing only, okay? That means if this is a positive value, that means your delta H system is greater than your T delta H system. If this is positive and we reverse, that is we are subtracting delta H system from this T delta S, that will be a negative value. That means it will be less than 0, which is written over here. Now, if we take the minus common, what will happen? It will become delta H system so it will become minus of delta H system minus T delta S, and this will be greater than 0. Your delta H minus T delta S is your gives free energy, that is your delta G. That means this will be greater than 0. This means for a spontaneous process, your Gibbs free energy change will be less than 0. That means your delta Z is your delta H minus T delta S. This will be less than 0 for a spontaneous process. Okay, so For a spontaneous process, your delta G will be less than 0. That is, change in Gibbs free energy will be less than 0, and this implies that your delta H minus T delta H will be less than 0. Here, delta H system is the enthalpy change of a reaction, enthalpy change of the reaction, and T delta S is the energy, and T delta S is the energy which is not available, the energy which is not available to do useful work. Okay, so your delta G is the net energy available to do useful work and is thus a measure of the free energy. So your delta is the net energy, is the net energy available to do useful work and is thus a measure of the free energy. Okay? And for this reason, it is also known as the free energy of the reaction. That means this is also known as the free energy for the reaction. Okay, free energy of the reaction. And if for a spontaneous process, your delta G is less than 0, if the process is non-spontaneous, that is for non-spontaneous processes, your delta G is greater than 0. Okay, this is very important that for a spontaneous process, your delta G will be less than 0, and for a non-spontaneous process, your delta G will be greater than 0. So this is how we can easily say whether a process will be spontaneous or non-spontaneous by seeing the value of the Gibbs free energy change. If it is less than 0, that is negative, that means the reaction will be spontaneous, and if it is greater than 0, that is having a positive value, that means the process will be non-spontaneous. Okay, so this is for this class. Okay, I am ending this class. In the last class, we will see the relationship between your delta G and delta S, and then after that we will solve some question, and then we will study the third law of thermodynamics.